Welcome back, everybody. Today we're going to be talking about modeling with exponential functions. What that means is pretty much real-life applications. Nothing too crazy, but something that's fun and I would say relevant. And all right, so in order to get warmed up, I think it's important that we also talk about just calculating basic percentages. This warm-up is not exponential growth, but it's a skill that we're going to be using in the lesson. So I thought I would spice this up a little bit and talk about the new iPad that, of course, you know. If you know me, you know that I love my iPad, and this new Pro looks pretty cool. So just the base one that I would like would cost $1,428. That's without the keyboard or the Apple Care or any of that stuff. And here in the state of New Jersey, we have a sales tax that's 6.625. So we should probably turn that into a tax rate. So usually what you do is you can divide that, because that's out of 100, right? So we have the rate is going to equal 6.625%. But then if you move that decimal place over, it goes here. And there we go. So that's important to remember. Two ways you can go about. What I want to know is, I'm not sure if I said this to you, but how much does the iPad cost with the tax? I don't want to know how much tax I'm paying, and just how much does it cost with the tax. So the fast way to do it, many of you know, is you just rather than taking 6% of the total and then adding it back, you can just multiply by 106% of the total, or in this case, 106.625. So let me show you the origin of why you're allowed to do the 106% technique. So the technique, the original one that I said, is just add the tax to the base price, which is something you would see on a receipt. That would make more sense. We're going to take our base price, which is $1,428, and we're going to add that to the tax 0.6625 times the original 1,428. And when you compute that, you get your answer. Now, since we're more interested in just the total cost and not actually really knowing what the tax is, I would like you to note that you can factor 1,428. So we can rewrite this now as A equals 1,428 times 1 plus 0.06625, which we know is A equals 1,428 times 1.06625. So it looks like it would be $1,522. Whoops. I say that a lot. Okay. So again, the moral to the story is 1 plus your rate of change can help you to, or your rate can help you shorten your work when you're trying to actually figure out a total with taking out that extra step of adding the tax or whatever. So that's for a growth, right? You're actually going to be paying more than the advertised sticker price. So another thing that I have interest in is I really like Tesla cars. I like electric cars, and so I was just looking at the Teslas don't have sales tax in the state of New Jersey, so that makes our calculation a little easier. And let's think of this hypothetical scenario where teachers could get a 15% discount for teacher appreciation for Teslas. So maybe they're only doing it for the Model Y. Who knows? So I looked on their website, and this is apparently the purchase price. Looks like for the extended range Model Y. So that's a pretty hefty cost there, $60,000. So $60,990. So say you were given a 15% discount on that. So that's really, since it's a discount, since it's like a negative rate, you could think of that as we can do the same exact computation in a way. I would say, all right, well, how much am I going to have to pay when I'm done? I don't want to know how much I'm saving. I just want to know how much I'm going to pay. So I'd go amount equals 60,990, and then minus, and it's going to be 0.15, right? That's the decimal equivalent of that percentage, times, again, 60,990. As with the last example, you see that we can factor out 60,990 times 1 minus 0.15. So the amount is going to equal 60,990 times whatever 1 minus 0.15 is, which is 85. Which really makes sense, right? It's 0.85. If you're getting a 15% discount, you should be paying 85% of the cost, right? So if you have a negative rate that you're trying to apply to something, a percentage of an original amount, and you want to know what your new amount is, you actually subtract that from 1 to get that more direct computation. So I wouldn't actually have to calculate the discount and then additionally subtract it afterwards, right? And I think a lot of you, if you've shopped for things, you've learned that trick. It's not so much of a trick, it just makes sense, right? So let's go do our computation. Okay, so there we go. So yeah, it looks like that's a pretty steep discount. Like, I mean, it's still expensive, but yeah, all right. So hopefully that was a good review for you. Moving on. All right, so here's the lesson. Obviously, there's your title, modeling with exponential logistic functions. We're not going to really get to logistic today. We're just going to talk about other ones, and then in the next lesson, we'll talk more about using a calculator and regressions and whatnot. Okay, so I thought again, let's just start this with an example before I start throwing functions, but formulas at you. So, all right. So here we want to come up with a function that would model this scenario. So we have so determine an exponential function with an initial value of 17, increasing at a rate of 6% a year. So let's make a little table here. That's like the best way to go about this. And then we can kind of see if we can come up with, it's just per year. So our variable t for time in years, and value, whatever the output is. So I guess we could just say it's like an amount. Just say A. So we're starting when t is equal to 0, we have 17. All right, and after 1 year, we're going to have 17 times 1.06, right? Because as just discussed in the do now, we know we're going to have 6% more than we had the year prior, which is going to be about equal to 17 times 1.06 times 1.06 is going to be 18.02. Cool. And then the next year, you're going to take that last amount and then you're going to do another 6% on top of that, right? So I would just come over here actually, and I'm going to multiply this number right here by another 1.06, right? That would make sense. So now I have 19.101. So really what we have though is we have this number, whoops, and we're just going to go multiply that again by 1.06, right? And that gave us 19.101. right? So then after a third year, we have 19.101, and we're going to multiply that again by 1.06 because it increases by 6% every year. Okay, or you could think of that as taking the last computation. If I leave it in this form, you can kind of start to see a pattern. And then let's multiply that by yet another 1.06, which gives us times 1.06, 20.247. Okay. And so on and so forth up to t years. So what's it going to give us? Maybe pause the video for a second, see if you can come up with a formula that would do that. Welcome back. So here we have our initial amount, and that's going to be times 1.06 to the t power. Okay, so let's test that out actually. We know that after 3 years we had 20.247 when we wrote that down, right? So we have a function now that says the amount of whatever substance or whatever this is going to equal 17 times 1. You know what, I'm just going to use a parenthesis. I don't know why I did that. 1.06 to the t power. 17 times 1.06 to the, in this case, we're going to do to the third power. And sure enough, it's 20.247 as we did manually there. Okay, so that's one example of how you could, the long way, figure out a pattern, right? So as it turns out, this is, like not a fluke. This is an actual method that you would utilize. There is a dog outside that's being really obnoxious, but it's not my dog, right? Anyway, so this is, if you look at this like textbook example that I found somewhere, you have this, they're talking about like a population. This isn't just apply to population, but if you had like an initial population, use p sub 0, and you can see how that population is growing using this sort of exponential model. But we know that 1 plus the rate is going to be our rate of growth, right? And then you could say ultimately, as you can see what they did here, I wonder if I highlight this in white, if that would help. You can kind of see it. But that's our final formula. So let's actually write that down more nicely. So it's going to say population with respect to time equals initial population times 1 plus the rate all to the t power. And it's just worth noting that we should, we can mark this up. So it's worth using this formula, that this is our initial amount. I say amount, in this case it's a population, it could be anything. So that's the initial amount. This is our rate of growth, or decay. So if r is a positive number, then you're going to get growth because you're going to add 1, like for example, a 6% growth. But if it was shrinking by 6%, then you would say minus 6%, and it would be like that 15% discount that I got on my hypothetical Tesla, right, for teacher appreciation. So Elon, if you're watching. Anyway, and up here, this is just like time, and sometimes it's years, sometimes it's days, it could be minutes, like, just some sort of time. Okay, so let's try this out. Or let's take a look at a couple examples, and they just want us to kind of break down these functions. So it says, tell whether the population model is an exponential growth function or an exponential decay function, and find the constant percentage of growth or decay. So first one, San Jose. We'll start with this. They say find the the constant percentage rate of growth or decay. So this one is going to be, okay, pause, I don't know. It's going to be growth, right? Because we know that that number there is greater than 1, the ultimate rate. So one way to get that rate, so we could even determine that, would be we have 1.0064, right? That's the number that is the base of our exponent. Let's just say just subtract 1 off of that so we can get our actual rate, which we know now r is going to equal 0.0064. Or you could say, move that decimal over 2 places, 1, 2, it's going to be 0.64%. So that's that first one. Just going to erase this just to, you don't really need it there. And then the next one, Detroit, we have that initial population times 0.985. So the base of our exponential function is actually a number that's less than 1, between 0 and 1. So we know that we're dealing with 1, and then we're going to go minus 0.58. So if you subtract, well, actually, I should probably go the other direction, right? So that's our number, and we're going to take away 1 from that, and that's going to equal 0.9858. 9858 minus 1. So that's negative 0.014. Negative 0.014. Okay. And if you move that decimal place over, the actual rate is going to equal negative 1.4%. Okay, so if your number base for your exponential function is between 0 and 1, we already studied when we're graphing them that's going to be it's going to be a decreasing function. So we know that we have some sort of like a decay, or some sort of I mean, you can't say population decay necessarily, but it's shrinking. So exponential decay, you would call that. And then if you have exponential growth, the number would be greater than 1. That's your base. Okay. Moving on. So this stuff's kind of, I think this is slightly more, I don't know, it's not like it's any more or less fun. I don't know why I like the bacteria type problems. So this is bacterial growth. Suppose we have a culture of 200 bacteria, and it's put into a petri dish, and the culture doubles every hour. So this is different. Rather than them giving us a percentage of growth, they're just saying it doubles every hour. Basically, I mean, I guess the rate of growth would be plus 100%, right? So it's basically, or it's 2 times every hour. 1 plus 1, right? It's 2. So predict the number n of bacteria, or predict the number n of bacteria will be present. So I think what they're trying to say is predict when the number n of bacteria will be 450,000. Okay, so we're starting with 200, and we're going to get up to 450,000, and it's doubling every hour. Okay, so that's pretty fast. So yeah, let's. One thing we know is it's our initial amount is 200, right? So we're going to say the amount that we have with respect to time, t is hours, equals number of hours, worth noting. So the amount of time, the amount of bacteria that we have relative to time is going to equal the initial amount, and that's going to be times 2, right? Because after 1 hour, we're going to have, let's just go back. At 0 hours, right, we're going to have 200 times 2 to the 0, right? So which is just going to be 200. Here, let's just go like this. times 2 to the first to the second, right? That's how we're going to compute every hour because it's doubling every hour, right? So after 1 hour, it's just going to be 200 times 2 to the first. After 2 hours, it's going to be 200 times 2 times 2, which is 2 to the second, so on and so forth. So we know that that's going to just be times 2 to the t power, right? So it's going to be a of t is going to equal 200 times 2 to the t. And then they want us to predict when the number n, okay, we're using, they said the number n. So I guess we're just going to call this n of t, and this should be a capital N. Sorry about that. So when will it be 450,000, right? So we're gonna want to use a calculator for this. I'd recommend Desmos, because I mean we could try to solve this, but it's it would definitely require some. Here, well, let me just show you what our process would be. So we want to know when and what is, for what t value do we have 450,000, right? So I'm going to say 200 times 2 to the t power equals 450,000. Okay, and we need to get t by itself. Haven't studied that yet. That's a further later section, but one way to solve a problem like this is to use a graphing calculator. And first thing we could do is just divide both sides by 200, because we're allowed to do that, order of operations. So these go away, and then half of 4,500. Just going to calculate it because I just don't want to get it wrong. Is 2250. So we want to know, when is 2 to the t equal to 2250? Okay, so let's go over to Desmos, and we're going to graph two functions. One, y equals, and then 2 to the x power, and then we're also going to graph y equals 2250, because I want to know when my exponential function actually intersects or reaches the value 2250. So let's just pan out. It's got to get all the way up there. There's that blue line. That's my other function. So now where these two lines intersect, or these two functions intersect, will be our answer. So when t is equal to 11.136, that's when our population should be there. So let's test it out. Let's go back to the original function and evaluate n of 11.136. Okay. So it's going to be 200 times 2. Here, let's go to this guy. 200 times 2 to the 11.136. 11.136. Yeah, this is going to be interesting. Yep. 11.136 2, and then 200 times. Okay, so that's 450,090. So that's a little bit off, but you also have to recognize we rounded to only 3 decimal places, and when numbers that are like really that big, things can get out of control. So, all right, last example. Here we go. So this is modeling radioactive decay. So it says, suppose the half-life of a certain radioactive substance is 20 days. So half-life is 20 days. So let's talk about what half-life is. So if you have a substance and they say that it has a half-life of a certain amount of time, after that time has elapsed, you have half the amount of what was there. So after 20 days for this particular scenario, we started with 30 grams. After 20 days, can you guess how many are left? If you guess 15, you are correct, 15 grams. So every 20 days, you have half the prior. if we can type that into this calculator, I have 30. After 20 days has elapsed, I now have 15, right? That's one half-life. So let's do another half-life. Let's take that previous answer and divide by 2. 2 half-lives. So let's divide that previous answer by 2. 3 half-lives. Divide that previous answer by 2. 4 half-lives. And you can just keep going on and on. Okay? So every single step is every half-life that goes by, you have half the amount of what was there prior. So this is a repeated multiplication thing. Every time you have a half-life, you multiply the previous. You're multiplying the previous, right, by a half. So that's repeated multiplication. And you saw me just divide and divide and divide. But another way to say division is multiply by the reciprocal. So yeah, you have that. So what they want us to do here is figure out how long is it before we have 3 grams of this substance remaining. You see from our little computations that we can see when we have 3.75, and we also see when we have 1.875, but when is it exactly at 3 grams? So we need to have some sort of relationship so we can solve that, as with the prior examples. So it says, suppose the half-life of a certain radioactive substance is 20 days, and there are 30 grams present initially. Find the time. So this one's a little bit tricky, so we're going to have to do a little bit of thinking here. We have the amount of time. So the amount we have with relative to time is going to equal, so we're curious about the amount, we're calculating amount, 30, that's the amount, the initial amount that we have, times 1/2, right? So I need this multiplication of 1/2 to coincide with 20 elapsed days, because we know that t is equal to number of days. And just for fun, I forgot to write the hours as the units on the last problem. Just FYI, you might want to go back and make sure that you recorded that. Okay, back to this. So starting out, if t is equal to 0, we know that 1/2 to the 0 is 1, so we have 30. Now we want this to be a 1, but t can't be 1, because if I let t equal 1 here, that means that after 1 day I have half the amount. I need after 20 days to have half the amount, right? So I need something to make it so that after 20 days, like I want to be able to plug 20 in. I need to be able to go a of 20 equals 30 to the 1/2 to the first power. So how do I write that t exponent with a constant involved so that when I plug in 20, it actually evaluates a 1? So maybe pause the video and try to figure that out. So we need to put t over some number here to get it to become, in this case, a 1. So if you guessed 20, you were right, because if I plug in 20 over 20 is 1, right? So if I were to plug in 40, that'd be 2 half-lives, right? If I were to plug in 40, that would be 40 divided by 20, which is 2. And then now I can multiply 30 by 1/2 squared. So that's 1/2 times 1/2, and then so on and so forth. So it looks like we figured this out. So we can actually say now our relationship is a of t is equal to 30 times 1/2 to the t over 20 power. Cool. That's pretty much half the battle right there. So since we have not discussed in this class how to solve an exponential function yet, we need to actually use a calculator as we did with the last one. We're going to say a of t equals 3. When does a of t equal 3? When 30 times 1/2 to the t over 20 equals 3. So let's graph that. So let me erase what's here. We're going to graph y equals You know what could even be more fun? Let's go f of x equals 30 times 1 divided by 2 to the x divided by 20 power. And we want to know, when does that equal 3? That's odd. All right. So when does that equal 3? So here we want to know so we can see that after after 66.493 hours, right? That's when we have 3. So in terms of half-lives, that's going to be 66 divided by 20, right? That's going to be 3 and change, right? If we go back to this problem here, you can see that after 1 half-life we had 15, after 2 half-lives we had 7.5, after 3 half-lives we had 3.75 grams, and after 4 half-lives we had 1.875 grams, right? So we knew that between 3 and 4, that would be our solution when we would actually hit 3 exactly. And if you look here, we have 66.439, and if I were to go 66.439 and divide that by 20, right? Because that's how many hours or days have elapsed. Divide that by 20 days and you get 4.321, blah, blah, blah. Okay, that's how many half-lives. They didn't ask us how many half-lives. I'm just saying, like, you can kind of get an estimate for how many 20s have gone by, right? So there you go. So T equals 66 days, so 66.439 days. 66.439 days. Okay. That was a long one, people. Hopefully that was helpful, and I'll see you in the next video.